So today we're getting away from integrals for a little bit to move on to a bit more of a general topic. So we're going to talk about limits today. So suppose that f and g are functions defined on the real numbers with the property that the limit as x goes to infinity of f is infinite, and the limit as x goes to infinity of g is also infinite. In this sort of situation, we can say without hesitation that the limit as x goes to infinity of 1 over f is going to be, well, 1 over a rapidly growing number, which is going to limit itself at 0. So we can abbreviate that just by saying that 1 over infinity is 0. No problem there. But what about the limit as x goes to infinity of g over f? The numerator is tending to infinity, but the denominator is tending to infinity as well. So we can abbreviate this sort of situation by writing down the fraction infinity over infinity. Now let's think about this a little bit. Essentially what we have here is a product. It is the function g times the function 1 over f. G is tending to infinity, by definition. 1 over f is tending towards 0. So taken together, this quotient g over f is subject to two competing forces. G is attempting to pull it to infinity, f is attempting to pull it to 0. So which one wins? Does this end up being infinity? Does this end up being 0? Or does it end up being something else entirely? Well, here are some examples of this sort of situation. So limit as x goes to infinity of x squared plus 1 over x cubed plus 2x minus 1. So here we have two polynomials. So as x goes to infinity, x squared plus 1 tends to infinity. X cubed plus 2x minus 1 also tends to infinity. So we have a limit that is of the form infinity over infinity. So this is the sort of situation that I've been describing. So if you recall from Calculus 1, we have a strategy for dealing with things like this. So the limit as x goes to infinity of a rational function. Namely, you divide the top and the bottom by the term with the highest degree. So for example, in all of this, the term with the highest degree is x cubed. So divide the top by x cubed, you get 1 over x cubed. Divide the bottom by x cubed, you get 1, 2 over x squared, 1 over x cubed, and then let x go to infinity. So this guy becomes 1 over infinity, which is 0. This becomes 0. This becomes 0. This becomes 0. This becomes 1. So we end up with 0 over 1, which is just 0. Okay, so in this situation, we appear to have a case where the denominator wins. The denominator is growing to infinity faster than the numerator is growing to infinity, and consequently, that pulls the entire limit down to 0. So in the competition between numerator and denominator, the denominator wins. Okay, here's another situation. Now we have a degree 5 polynomial on top, a degree 2 polynomial on the bottom. Well, same as before. Divide the top and the bottom by the term with the highest degree. In this case, the term with the highest degree is x to the power 5. So this is what happens. This goes to 0, this goes to 0, this, and this all go to 0. So we end up with 1 over 0. And furthermore, the denominator is always going to be positive. So it's going to 1 over 0, but it's approaching 0 from the right. Yeah, it's approaching 0 from the positive side. So that means that we're going to end up getting positive infinity. If this was approaching 0 from the negative side, this would be negative infinity. But point being, this is the exact opposite situation. Up here, we had infinity over infinity, but it ended up evaluating to 0. Here, we have infinity over infinity, but it ends up evaluating to infinity. So this is a case where the numerator wins the battle. So the numerator is stronger than the denominator and pulls the entire thing up to positive infinity. Here we have yet another example. Here, the degree of the top and the bottom is both 3. So the The highest exponent is 3, so we divide the top and the bottom by x cubed. And we end up with this. So this goes to 0, this goes to 0, this goes to 0, and we end up with 2/7. So the ratio of the leading coefficients. So we see here that whereas you can take something like 1 over infinity and confidently say that that's 0, you cannot say the same thing about infinity over infinity. You cannot confidently say that this dude is going to equal 0, or that this dude is going to equal infinity. Because here we have 3 examples where the same form ends up taking vastly different identities. Here it's 0, here it's infinite, and here it's some random number. So because of that, we call this form, or limits of this form, indeterminate. Indeterminate. That means that by itself, this symbol signifies nothing. This symbol by itself signifies nothing, because the limit from which it arises can end up evaluating to 0, infinity, or indeed any real number. So when you encounter a limit that has the form infinity over infinity, basically you need more information to be able to determine what that limit actually is. So to sort of summarize the example above, if you encounter an indeterminate form that has arisen from a ratio of polynomials, then in that case at least it is easy to figure out what's going on. So as I was alluding to in the example, really it just depends on the degree of the numerator and the degree of the denominator, respectively. So if the degree of the numerator is bigger, then the numerator wins. The numerator goes to infinity faster, so to speak, and that pulls the whole thing to infinity. If the degree of the denominator is bigger, then the denominator wins and pulls the whole thing down to 0. And if the degrees are equal, then they balance each other out in some sense. And the limit just ends up being the ratio of the leading coefficients. So like here, the leading coefficients were 2 and 7, so it ended up being 2/7. So that's how we deal with infinity over infinity when it comes from a ratio of polynomials. But, of course, there are many other ways that we can obtain a limit of the form infinity over infinity. For example, we might have something like this: natural log x over x squared. So as x goes to infinity, the natural log explodes, albeit very slowly. And as x goes to infinity, x squared also explodes. So what do we do in this situation? I mean, our strategy up here isn't going to work because these guys aren't polynomials. Natural log isn't a polynomial. So infinity over infinity is indeterminate. 0 over 0 is also indeterminate. Indeed, if we have infinity over infinity arising as some limit of f and g, well, we can just rewrite this a little bit. If we divide the top and the bottom by g, and then divide the top and the bottom by f, we end up getting this. And then if g tends to infinity, then 1 over g tends to 0. If f tends to infinity, then 1 over f tends to 0. So infinity over infinity can always be rewritten to be of the form 0 over 0, and the other way around as well. Any limit of the form 0 over 0 can be rewritten to be infinity over infinity. So that means that these guys are both indeterminate, meaning that by itself the symbol means nothing. We need additional context. So we need some sort of systematic way of evaluating indeterminate forms when the limit involved is not the limit of a rational function. Because in that case, that it's easy. You just follow this rule. So this is what L'Hopital's rule supplies to us. L'Hopital's rule supplies us a means of evaluating limits of the form infinity over infinity or 0 over 0. So, in particular, so suppose we have a limit of the form 0 over 0 or infinity over infinity. Then, as it happens, this limit is the same as the limit you would get if you replace the numerator with its derivative and the denominator with its derivative, provided this limit exists or it becomes plus minus infinity. So this is interesting because remember what the derivative means in a physical sense. Like derivative refers to a velocity, derivative refers to rates of change, rates of growth. So what L'Hopital's rule is essentially telling us is that when we have this sort of situation where the functions f and g are competing with each other, one is trying to pull it to infinity, the other is trying to pull it to 0, all that really matters is the rates at which f and g change. The thing which determines which side is going to win is information about the derivatives. So I'm not going to prove L'Hopital's rule because there's a lot of special cases that you have to go into, and it's not terribly interesting. So yeah, we're just going to leave it at that. Suffice to say that it only works if you have 0 over 0 or infinity over infinity. And needless to say, these functions need to be differentiable as well, but, all the functions that we encounter are like that. Okay, so some examples. So this is pretty easy, because basically you're just differentiating the top and the bottom, and then seeing if the limit becomes any easier to deal with. So first off, we need to verify that L'Hopital's rule is applicable by seeing if this limit is of the form infinity over infinity or zero over 0. Right, L'Hopital's rule only works if that is the case. So let's go ahead and naively plug in the limit point. So in this case, the limit point is x equals 1. So log 1 over 1 minus 1. Well, indeed, log of 1 is 0, 1 minus 1 is also 0. So we get 0 over 0. So L'Hopital's rule is applicable. Okay, so L'Hopital's rule then says to replace the top and the bottom by the derivatives of those respective functions, and then see what happens. So the derivative of natural log is 1 over x. The derivative of x minus 1 is 1. Okay, well, that's easy enough. Clean that up a little bit. And this is just 1 over x. And now we have no problem evaluating this limit at all, because all we need to do is plug in x equals 1, and yeah, we got 1. So nothing strange happens. So there's our answer. The limit is 1. So once again, first we need to verify that this works by quote-unquote plugging in the limit point. So here we're plugging in infinity. So let's see. I know this isn't strictly the best notation because infinity isn't a number, but really what we're doing is we're taking the limit as e to the x goes to infinity. Here we're taking the limit as x squared goes to infinity. So e to the x, of course, goes to infinity. That explodes. X squared also explodes. So we get infinity over infinity, which means that L'Hopital is justified. Okay, so let's replace the top and the bottom with their derivatives. So the derivative of e to the x is e to the x. The derivative of x squared is 2x. Okay. Well, now if we attempt to plug in infinity again, well, we get infinity over infinity yet again. Right? E to the x explodes, 2x also explodes. So we need to use L'Hopital again. That's easy enough. You know, you may need to use L'Hopital many times, but that's fine. So derivative of e to the x is e to the x. Derivative of 2x is 2. All right, so now e to the x explodes to infinity, and that is that. So this is no longer indeterminate. This is just infinity. So nothing strange going on here. So this limit is infinity. And we are done with this one. Okay, next. So if we plug in infinity, we get, so natural log of infinity is infinity. Cube root of infinity is also infinity. So L'Hopital's rule is justified. I mean, I know that I'm seeming pedantic here, but this really is important. Like, L'Hopital's rule only works if you have either infinity over infinity or 0 over 0. Okay, so let's replace the top and the bottom with their derivatives. So log x, derivative of that is 1 over x. Cube root of x, this is x to the power 1/3. So use the power rule. 1/3 minus 1 is negative 2/3. Now we can clean this up a little bit by canceling the exponents. Also, we're dividing by 1/3. Dividing by 1/3 is the same as multiplying by 3. So we can just pull that 3 right out. Let's see. So we've got a negative 2/3 on the bottom, which means I can put that on the top. And then we have a 1 over x, so I can put that x on the bottom. So 2/3 minus 1 So we end up with, okay, so 2/3 minus 1, that is negative 1/3. So we end up with this. Okay, so this denominator explodes to infinity, so we have 1 over infinity, which is 0. Or 3 over infinity, but whatever, same deal. Okay, so this whole guy ends up being 0. So we can interpret these results in a way which is maybe more intuitively satisfying. So like over here, we saw that the limit ends up being 1. So we can sort of say that that means that natural log x and x minus 1 approach 1 at the same rate. So neither one is necessarily any faster than the other as we approach x equals 1. Over here, e to the x over x squared, that ended up being infinity. So that means that as x goes to infinity, e to the x wins. That wins the tug of war. So e to the x explodes much, much faster than x squared does. Over here, this guy ended up being 0. So that means that the cube root of x wins in the tug of war. So that means cube root of x explodes to infinity much faster than the natural log does. Right, so all of these results you can sort of interpret in terms of like one function being stronger than the other, so to speak. Where by stronger I mean approaches the limit faster. Okay, so what's going on with this one? So plug in the limit point. Let's plug in 0 to see what happens, because we have to make sure that L'Hopital is justified. So let's see. So tan 0 minus 0 over 0 cubed. Well, tan 0 is equal to 0, so we end up getting 0 over 0. So indeed, L'Hopital is justified. So let's go ahead and take the derivative of the top and the bottom. Okay, so derivative of tangent is secant squared. Derivative of x is 1. Derivative of x cubed is 3x squared. Okay, so now let's plug in 0 and see what happens. So secant squared at 0 minus 1 over 3 times 0 squared. So secant, that's 1 over cosine, right? So cosine at 0 is 1, so that means this is also 1. Huh, so we get 0 over 0 again. So let's use L'Hopital again. So what is the derivative of secant squared? So that is, so we have to use the chain rule here. So that is 2 secant, so that's differentiating the power, times the derivative of secant, which is secant tangent. Like so. Derivative of minus 1 is just 0. Derivative down here becomes 6x. So it seems like, once again, we're going to end up getting 0 over 0. Right? Because tan at 0 is 0. Plugging in 0 here gives 0 as well. Now, we can actually do a little bit better than that, though. Because the thing is, I don't want to differentiate this again. I mean, we're getting 0 over 0, so we know that L'Hopital's rule is still justified. But the thing is, differentiating the bottom, that's fine. That's just going to become 6. But differentiating the top, I don't know. It's going to get really ugly. So you know what I want to do? Let's rewrite this a little bit. So before using L'Hopital again, let's rewrite this a bit. In particular, this is the same as, okay, so let's see. 2 over 6 is 1/3, so already I can just pull that out. We have secant squared of x times tangent over x. And really, the problem is arising from this term here, right? This tan x over x, that's where the problem is coming from. That's where the 0 over 0 is coming from. But the secant squared is fine. If I plug in 0 here, we just get 1 over cosine squared at 0, which is just 1. So this is the same as 1 times all of this. So let me write it like this. Like so. And this is perfectly valid. You can distribute the limit over products like this, provided these limits all exist. Which, to be fair, we don't exactly know if this limit exists yet, but we're about to find that out. In any case, this dude here is just 1. So, yeah. So that is a pretty significant simplification. Okay, so now let's use L'Hopital. Writing all these limits is a bit of a pain, but so it goes. So derivative of tangent is secant squared. Derivative of x is 1. Ah, well, happy day. Finally we end up with something which doesn't just keep on recursively giving us L'Hopitals, because plugging in 0, you just get 1 here. So we get 1/3 times 1, which is just 1/3, and we're done. So yep, so there's that. Yeah, so that's that. All right, one more of this form. So what happens when I plug in pi into these guys? And we are approaching pi from the left. Well, let's see. I mean, the fact that we're approaching pi from the left doesn't really matter. So sine at pi is 0. Cosine at pi is -1. Oh. So, this one was a bit of a red herring. So this one's just 0. It's just 0. So we don't need to do anything else. So yeah, this one was sort of put in here, I guess, to illustrate to you that you shouldn't like just because you see a limit that has a ratio in it, that doesn't necessarily mean that L'Hopital is immediately viable. You should always start by just plugging in whatever the limit is, and if you end up getting something well defined, then cool, you're done. You don't need to do anything else. L'Hopital is only applicable if you get 0 over 0 or infinity over infinity, and this example here is just, to show you that. Okay. So, we have seen that limits of the form infinity over infinity and 0 over 0 are indeterminate. And what that means is that by themselves, those symbols don't mean anything. We need the additional context of the limit that they came from to be able to learn anything about it. And these things are indeterminate because there is some sort of competition at play. There's a competition between the component parts. So this bit on the top is trying to pull it to infinity. This bit on the bottom is trying to pull it to 0. So there's a tug of war happening. Similarly with 0 over 0, the 0 on the top is trying to pull it to 0. The 0 on the bottom is trying to explode it to infinity. So, they're pulling in opposite directions. Which one wins? Well, we can get other indeterminate forms by looking at other limits where there is this sort of competition at play. So, for example, limits of the form 0 times infinity are also indeterminate for exactly the same reason. This guy is trying to pull it to 0, this guy is trying to pull it to infinity. So, which of those ends up winning depends on the functions that go into making this limit. So if you end up getting an indeterminate form of the form 0 times infinity, the idea here is to rewrite the limit, to do some sort of algebraic manipulation, so that it ends up being in the form 0 over 0 or infinity over infinity, and then we'll be in a position where we can use L'Hopital's rule. So that is the idea, is to rewrite this thing so that L'Hopital's rule becomes applicable. So first off, for this one, let's plug in x equals 0 to see what happens. Well, we get 0 times log of 0. And remember, the limit as log approaches 0 is negative infinity. So this is 0 times negative infinity. So this is indeed of this form. I guess I should put a plus minus here. Yeah. So this is of that form. So we need to rewrite this so that L'Hopital becomes viable. So how can we do that? Well, we want to rewrite it as a fraction. So one trick that we can use to do that is to take this x and rewrite the x to be 1 over x. Like so. Right? I mean, that's perfectly fine. Dividing by a fraction is the same as multiplying it by its reciprocal, so this dude and this dude are identical. And now, if we were to plug in 0 naively, we get log of 0, which is negative infinity, and 1 over 0 here, which is, okay. My computer stuttered for a moment. I thought it was going to stop recording. Maybe in another couple minutes. We'll see. So 1 over infinity is infinity. Or, I'm sorry, 1 over 0 is infinity. We're approaching from the right, so it is positive infinity. So now, indeed, we are in a position to use L'Hopital's rule, because it's infinity over infinity. The presence of this sign doesn't really matter. And it is important to recognize that we are not using L'Hopital on the original thing. I mean, indeed, that wouldn't even make sense because it has to be a fraction. We are using L'Hopital on the rewritten version. So let's see. The derivative of log is 1 over x. The derivative of 1 over x, so this is x to the power negative 1, so we can hit this with the power rule, and we get minus 1 times x to the negative 2. So that's minus 1 over x squared. Now we can clean this up a little bit. So bring this x to the bottom, bring this x squared to the top. So one of these x's cancels. And we just get negative x. All right, and now we can plug in 0 with no problem at all. So there we go. There's our final answer. It's 0. So basically what this tells us is that in the competition, x log x, x is desperately trying to go to 0. Log x is desperately trying to go to negative infinity. In this competition, x wins. X wins because x ends up pulling the whole thing down to 0. So that means x is a lot stronger, so to speak, than the natural log function is. And indeed, that's going to be the case of any polynomial. Polynomials are always going to be stronger in this limiting sense than the natural log function will be. You will find that that is a common occurrence. Okay, let's take the limit as x goes to negative infinity of x e to the x. So let's plug in negative infinity to see what's going on here. So here we have negative infinity times e to the negative infinity. So for the exponential function, as we go to negative infinity, this becomes 0. So indeed, we end up getting an indeterminate form of the form infinity times 0 again. So we rewrite to be a ratio, and then hopefully L'Hopital will be applicable. So, how should we rewrite this? Well, based on the previous example, you might think, okay, well, let's take x and rewrite it as 1 over 1 over x, right? Okay, well, indeed, this is going to make L'Hopital applicable, because then e to the negative infinity is 0, 1 over negative infinity is also 0, so then by L'Hopital you would get, so derivative of e to the x is e to the x, derivative of 1 over x is minus 1 over x squared. Oh, well, that's no good. We still get 0 over 0, right? One would have hoped that in using L'Hopital's rule, this would become simpler. Alas, it has not. Indeed, we get 0 over 0 again, so we can use L'Hopital again, but then the denominator here is just going to become a power of 3. Okay, do it again. Denominator is going to become a power of 4. Do it again, going to become a power of 5. Okay, well, this is just going to keep on going forever. So this was not a very good choice. So we could do L'Hopital again, but we're just going to keep going forever. A better choice would be to rewrite like this. So instead of taking x and writing that as 1 over 1 over x, let's take the e to the x and write 1 over e to the x. I mean, we pretty much only have those two choices, right? So now keep the x on top, and on the bottom we have 1 over e to the x. Well, so that's the same as saying e to the negative x. Now, indeed, so on the top we get negative infinity, and on the bottom, if we plug in negative infinity, we have negative infinity, so that's positive infinity, and e to the positive infinity is infinity. So we can do L'Hopital on this guy, and we shall see that it ends up being a lot more amenable. So the derivative of x is 1. The derivative of e to the negative x is negative e to the negative x. Okay, and now when we plug in negative infinity, we get e to the positive infinity, which is infinity. So 1 over negative infinity is still 0. So there we go. There's our answer. It is 0. So one way that we could interpret this is that in the tug of war, so x is trying to pull this thing to negative infinity. The exponential function is trying to pull it to 0. The final answer is 0, so that means the exponential function wins. So the exponential function is stronger than x. So we can kind of see a hierarchy of functions being developed out of these examples. A hierarchy of function strengths, relative function strengths. Because natural log was weaker than x, but now x is weaker than the exponential function. And indeed, this is going to hold in general. So really, we can replace x with any polynomial, and the same result would hold. So natural log is weaker than polynomials, but polynomials are weaker than exponential functions. That is a general truth. At least, well, yeah, that is generally true. Okay, so this was the indeterminate form of the form 0 times infinity. Another way to get indeterminate forms is to have infinity minus infinity. This is indeterminate, again, because we have this sort of competition happening. You know, this guy is trying to pull it to infinity, this guy is trying to pull it to negative infinity, and who wins? You know, if this guy is stronger, then it might go to infinity. If this guy is stronger, it might go to negative infinity. And if they are approximately the same, then it might end up going to 0. Or it might end up going to some other real number, right? Where these guys balance each other out to some extent. So here is an example where that's going to happen. So let's plug in x equals pi over 2. So secant at pi over 2 minus tangent at pi over 2. So let's see, secant is 1 over cosine. Cosine at pi over 2 is 0. So we have 1 over 0. And we're approaching from the left, so that would be positive. Right, if you look at a graph of the cosine function, as we approach pi over 2 from the left, we see that it's always positive. As for tangent, so tangent at pi over 2 is positive infinity. Right, because this is where it has a vertical asymptote. And again, since we're approaching from the left, it goes to positive infinity. If we were approaching from the left, it would be negative infinity. In any case, this is positive infinity, and we're subtracting another positive infinity from it. So it's indeterminate of this form. So similarly to the examples coming before, our strategy here is going to be to try to rewrite this so that it looks like a fraction. In which case, hopefully L'Hopital's rule becomes applicable. So let's see, how can we rewrite this thing? Well, let's take advantage of our knowledge of trig identities. Oh, the bottom didn't copy, huh? So let's see. Secant is the same as 1 over cosine. Tangent is the same as sine over cosine. Oh, so how convenient. The denominator is the same. So we can go ahead and combine these guys. There we go. Now it'll copy. So the denominator is cosine, and the top is 1 minus sine. So now, when we plug in pi over x, what the heck? Pi over 2. Okay, so now when we plug in pi over 2, what do we get? Well, sine at pi over 2 is 1. So we have 1 minus 1, which is 0. Cosine at pi over 2 is also 0. Okay, cool. So we got 0 over 0, which means that we can now apply L'Hopital. So we are going to do L'Hopital on this dude. So the derivative of 1 minus sine x. So derivative of 1 is 0, so that goes away. Derivative of sine is cosine. Derivative of cosine is minus sine. Okay, so these minuses go away. And if we plug in pi over 2, we get 0 over 1. So 0 divided by 1 is just 0. So there we go. We're done. So, interestingly enough, we had this situation where it was like infinity minus infinity, and perhaps as expected, it ended up being 0. So these guys, in fact, perfectly canceled each other out. But you can't rely on that, right? Infinity minus infinity, in general, may not be 0. So I kind of would have liked for them to put an example of that in here, but yeah, so it goes. So, one more class of indeterminate forms may be obtained from powers. And again, the common theme behind all the indeterminate forms is that it is a limit where there is some sort of competition between the two factors. So, the following are indeterminate. So if you have some limit which ends up giving you 0 to the power 0, well, this base of 0 is pulling the whole thing to 0, but the exponent of 0 is trying to pull the whole thing to 1, right? Because anything to a power 0 is 1. So it's being pulled to 0 in one direction, pulled to 1 in the other direction. So it's indeterminate. Not sure which direction wins. Infinity to the 0 is indeterminate. The base pulls it to infinity. The exponent pulls it to 1. 1 to infinity is also indeterminate. The base pulls it to 1, because 1 to any power is 1, but the infinity tries to pull it to infinity. So for indeterminate forms of this type, again, we're going to want to try to rewrite it so that L'Hopital's rule becomes applicable, but it's a bit less obvious how we can actually do that. So what we're going to end up doing is we're going to take advantage of the laws of logarithms, specifically to take this exponent and move it out front, right? Anytime we have an exponent which is being problematic, we like to take advantage of the laws of logarithms to take that exponent and pull it down. That's why logarithms are important and just generally useful, because they let us take exponents and pull them down. So let me show you what I mean by that. So here, so we got this mess. So what happens if we plug in x equals 0? Well, we get 1 plus sine 0 to the power of cotangent at 0. Sine 0 is 0, so the base here is just 1. Oh dear. Okay. I accidentally went full screen for a second. That was scary. So the base is just 1. What is cotangent at 0? So cotangent is the same as 1 over tangent. Tangent at 0 is 0, so this is 1 over 0, so that's infinity. Okay, so we got this form here. So here's what we're going to do. Let us take this limit, and we're going to give it a name. Let's just call it y. So let's let y be this limit. We will assume that the limit exists, but that's not too hard of an assumption to make. So let's give this limit a name. And now let's take logarithms of both sides. So of both sides of this equation here. Because then, once we have a logarithm over here, that's going to allow us to take this exponent and move it out front. So ultimately, we want to determine what y is. But as an intermediate step, we're going to figure out what its logarithm is instead. And an important thing about logarithms and limits is that a logarithm is a continuous function, which means that you can take that logarithm and just put it inside the limit, and don't worry about it. So since log is a continuous function, we may write log of a limit of junk, say f of x, is equal to limit of the log of f of x, right? So limits and logs, those are interchangeable, which means that log of the limit, well, I can just flip them around and write the limit first. Like so. Alrighty. And then, as desired, we can take this cotangent and pull it out front. And what is left over? 1 plus sine 4x. Okay, so now that we have a product, what happens when we plug in 0? Well, cotangent of 0, as we have already determined, is infinity. And if we plug in 0 here, we have log of 1 plus 0, so that's log of 1, which is 0. So, cool. By taking logarithms, we have managed to transform an indeterminate form of type 1 to infinity into an indeterminate form of type infinity times 0. And these we know how to deal with, because these we can rewrite to be a fraction. And once we have it rewritten as a fraction, we can then apply L'Hopital. So, how do I want to rewrite this? Well, cotangent is the same as 1 over tangent, so I can just reference that fact immediately. Right? So now what happens when I plug in 0? So now I get log 1, which is 0, and tan of 0, which is 0. So cool. Now we are finally in a position where L'Hopital is actually applicable. So don't forget this left-hand side, because we are working with an equation now instead of a single expression. This is important because at the end we're going to want to solve for y. Okay, so what's the derivative of the top? So we're going to have to do the chain rule here. So derivative of the log is 1 over all of this stuff. And then we have to multiply by the derivative of 1 plus sine 4x. So 1 becomes 0, sine becomes cosine. But then we have to multiply by the derivative of 4x, which is 4. Okay, that's the derivative of the top. Derivative of tangent is secant squared at x. And now, in fact, we can plug in 0 with no problem, because as we've already established, secant at 0 is 1 over cosine at 0, which is 1. So squared is still 1. Plug in 0 here, this disappears. Plug in 0 here, this becomes 1. So this all just ends up being 4. So finally, all that we need to do is solve for y. And that's easy enough. To get rid of the natural log, you just take e and raise it to both sides. you take e raised to both sides of the equation. Right, because y is really what we were interested in the first place. So e to the power log y equals e to the power 4. And indeed, on the left, this e and this log cancel, so we get e is equal to e to the power 4. Or y is equal to e to the power 4. So there we go. So there's our limit. So this weird thing, amazingly, strangely, unbelievably, ended up having Euler's number attached to it. It's part of the mystery of Euler's number and why it's really so... part of why it was so incredible. Yeah, I mean, I guess it shouldn't be terribly surprising that Euler's number makes an appearance since we're talking about exponential functions, and e is sort of at the core of everything having to do with exponents and their calculus. Okay, so one more example, and this one we're going to attack by using the same strategy of taking logarithms. So if we plug in x equals 0, well, we get 0 to the power 0, which we have already established is indeterminate. So what was our strategy? Well, let's give this limit a name. Let's call it y, or L, or whatever you want. And then take logarithms of both sides. So log y is equal to the limit of log x to the x. I can pull that log inside the limit because it's continuous. Now, use the laws of logarithms to take this x and move it out front. And, oh hey, I think we've seen this one already. Limit as x goes to 0 of x log x. Yeah, there it is. Limit as x goes to 0 of x log x. So we've already established that this guy is equal to 0. So we don't have to go through that again. So that was example 6. Yep, because x is much stronger than the natural logarithm. So in the race to 0, this guy is going to 0, this guy is going to negative infinity. The x is stronger, so the x gets what he wants. And then finally, just solve for y. So take e to both sides. So on the left it cancels, and on the right e to the power 0 is just 1. So that's neat. You wouldn't necessarily expect that this dude, x to the x as x goes to 0, that this equals 1. I mean, I guess if you were to look at this as a competition, this base of 0 is trying to pull things to 0. This exponent of 0 is trying to pull things to 1. This tells us that the exponent was stronger. The exponent won that battle. It's an interesting way to think of things, I think. Okay, so that's all for L'Hopital's rule. I think that covers all of the possible applications that you are likely to see. So, just as a review of all the indeterminate forms, so infinity over infinity and 0 over 0. 0 times infinity. infinity minus infinity, and then these powers. Those are all the indeterminate forms that you can run into. And the strategy for each one is to rewrite it in such a way that L'Hopital becomes applicable. Yep, so that's it for this one.